Okay, so let's do some clustering. So all that's just setting the stage, and so I'm now going to finally give you a clustering algorithm, and it'll feel like we're doing something. Okay. So I am going to put on the slide here the full algorithm for k-means, but I'm not going to talk through it right now. I'm actually just going to do it by example. So this data is what we're going to try to cluster, and so just looking at it, how many clusters do you see? What do you think? 2, okay? Anybody think, okay, 2. Anybody think they see more clusters? Anybody recognize this data by any chance? Maybe not. I see it a lot. So this is actually our iris data set with the versicolors, virginicas, and setosas. So one could argue there's actually 3 clusters. There's the setosas down here, and then the orange and green ones from the versicolor and virginica. But you can't really see them here. Okay. So 2. 2 is probably the right answer, just looking at it. But even though in reality there's 3 classes that this data was drawn from. Okay, so how does k-means work? Well, I'm going to pick a k. You guys picked k equals 2, so let's go with 2. And that's also what I put on the slide. Good. And so I'm going to pick 2 arbitrary, what I'll call centers. There's a blue one and an orange one. How did they get there? I just randomly picked. Those are their locations. That's one approach. So I've decided that this is a blue center, this is an orange center, and what does that mean? Okay, well, what I'm going to do is I'm going to look at each point, and I'm going to say, actually, I'm going to ask you a question. Which point is this closer to, the orange or the blue center? Orange. Okay, we'll make that one orange. How about, I don't know, this one? Blue. Okay, it's kind of hard to tell, but it's blue. And so if you do this process of going through every point and saying which one it's closer to, you end up coloring the points blue and orange as shown. Okay. Now, one little issue I should note is that the axes are not on the same scale, so your sense of distance might seem a little skewed. That is, each unit of width here, this is, actually look here, this is 7, and this is 2.5. So maybe I could have put it on the same scale, but I didn't. Okay. All right. So that's the first step. So that's the clustering I have. Do you like this clustering? No, it's not that good. Why is this clustered here? It feels like this should be one and this should be another maybe. So what we're going to do next is we're going to take the centers and move them to the middle of their buddies. So these are the actual members of the kingdom of orange, and so we should really move the center to the middle. Likewise with the blue here. Okay. So where should they go? Just like think about it just for a second. Try and predict where they're going to go with your eyeballs. Okay. All right. So it turns out they go there and there respectively. So that's the new position for the centers. So what happened was we moved our centers to be in the middle of the points whose color correspond to the centers. Okay. Now this is an iterative algorithm, so we're going to repeat that process. And so I'm going to do the exact same thing. I'm going to say, well, orange, you're now in the middle of all these dots, and blue, you're over here. Let's color every point according to which center it's closer to. So if I do that, I now have this clustering. Is this one better than the one we had before? Yeah, all right, and go back to. Okay, that's the old one. This is the new one. That seems better. Okay, so we've colored all the points, but now orange is kind of stuck over in this corner. It should be a little bit further down here, maybe. So if I move the centers again, okay, let's do it a couple times. So I'm just moving the centers. So going to iteration 1 to iteration 2. The centers are moving closer to their center of mass. Okay, you can see what this algorithm is doing. It's kind of your centers are going to slowly gravitate towards places they should be. Okay, it's heuristic, but it's doing something useful. All right, again, we color all our points according to which center they're closest to. That's what we get. All right, next we move the centers. Okay, notice the centers aren't moving as much now. So I'm just doing those so you can watch the orange and the blue. Okay, so the centers have moved to their new position. We color the points. Okay, I've got one lone holdout over here. Why is this one blue instead of orange? Because it is closer to this star than this star. So this distance is a little closer. All right. So then we move them one more time. So notice the centers are just barely moving, 4 to 5. Like look at the orange star. Okay. Okay, there you go. All right, so we've reached position 5. We color all the points, and we end up with that. Okay. You'll notice that this is the same as we had before. This is iteration 4. This is iteration 5. The centers are in a slightly different position, but the colorings are the same. So question for you. We see the results after iteration 4 and 5 here. The centers moved ever so slightly, but none of the points changed color. So do you think we are done? Okay. Are we done? All right. Turns out the answer is yes. And so the reason is, let's say we tried to do iteration 6. Since none of the points changed, right? So here we go, iteration 4 to iteration 5. This star has moved ever so slightly down and to the left. And now it is at the center of the orange points. And blue is at the center of the blue points. Okay? If I tried to move the blue star to the center of the blue points now, what would it do? It would stay in place. Likewise with the orange. Like they're in their place. There's nothing else to do. Okay? So the fact that we didn't change any labels means we are done. Yeah. So the question was, do we need to check that the centers don't move? You do not actually need to compute the new center positions. You can simply say the labeling is exactly the same as before, though it may be programmatically, when you're writing code, more convenient just to do the next step and see, oh, well, the centers didn't move. Okay. So I would say that while I think the best answer is yes, you might have said, well, let's just do like a half step more. Okay. So that would be a fair answer too. All right. So I was a little ambiguous in my question when I said, are we done? But what I mean by we're done is that there's no way that any colorings will ever change again. If you ever have a situation where in iteration 4 you have a certain set of colors, and then in iteration 5 you have the same set of colors, it will definitely not change ever again. You're locked in because the centers won't move. Now I should note, just briefly, that you may have heard of something else called k-nearest neighbors. I'm not going to talk about that algorithm today. So k-means, what we were discussing today and will continue to discuss, is not k-nearest neighbors. And I only mention this because sometimes people learn them and get confused. So k-means is a clustering algorithm. It assigns points to one of k clusters. K-nearest neighbors is a classification technique that is related in some way because they both involve the notion of distance. But really the main thing they have in common is the fact that they start with the letter k in their name and have a dash. Okay, so not really the same thing. All right, just mentioning that. All right. So let's talk about something called distortion. So hopefully, actually, everybody happy with what k-means does? So provides you clusters. Yes, please.
What if you pick a different k? So if we had k equals 3,
yes.
we still only have, or apparently there are 2 clusters.
Yes.
What if we had more, like a higher k?
Yeah, so the question is, what happens if we have more k's? And so we'll talk about that because I picked k equals 2. And the very last topic of our day is how to pick k. Okay, great question. All right. Yes? Mm-hmm. So the question was, if you pick a different starting point, a different starting center, can the results be different? They can be different, and we'll see that they could be different. In this specific case, I'm not sure, because it's so... The structure of the problem is such that I think it might always go to the same place, but I'm not sure. But in general, it does not have to converge to the same point.